Hey everybody, and welcome to another episode of Space Science with Python. Today we are going to dive into the fourth script of our Meteor project, and today we are going to consider four different directions in the sky: the sun direction, or so-called Helian direction, the anti-Helian direction, the apex, and anti-apex. Now, if you recall from last time, we created a distribution of the night sky where we have seen the radiance moving over time in a certain direction, so over the entire sky, and we saw that also the impact velocity of these meteors were also following a certain distribution, like the high velocity particles were focused at one point and the lower velocity at another point, and then they were moving. And with the four directions we try to understand why. And I would say let's dive directly into the code so that we get a good understanding at the very end of the script. So instead of talking about the theory a priori, let's talk about it at the very end. Now, the script is pretty simple and also recycles parts from last time, where we have our where we load in the meteor data, we create our date time column, we have also the day of year column, and so on. But today, for this Helian, anti-Helian, apex, and anti-apex direction, we need SPICE. So SPICE is a library from NASA. I talked about it in my previous videos. It's a pretty mighty library to compute, let's say, anything that has to do with geometry in the solar system. Positions from planets and asteroids, rotation of these objects, orbital elements, the orientation of a spacecraft, and what have you. So everything, basically. And SPICE needs certain kernels to start computing things, and these two kernels are loaded here in this script. The very first one is the time kernel. So time is not as trivial as we have it here now for 1500, so for 3 p.m. in the afternoon on a Sunday. Time is a little bit more complicated. It's also considering relativity effects, and so on. So we need this kernel for time computations, and we need also a kernel that contains some positional information of our major planets and also the sun and the Earth. Now, SPICE understands only a certain time format. It's called ephemeris time, and this is what we do in this cell here, where we convert the daytime into this ephemeris time. The ephemeris time is like the seconds that passed J2000, so the seconds since the 1st of January 2000 of the year 2000 at around 12 o'clock in the afternoon. Now, what we do now is we compute the Helian, the apex, the anti-Helian and anti-apex directions, and this is what we do in this cell. So we use a SPICE function called spkgps, and spkgps provides you the vector from an observer to the target. So we have here the observer is 399, this is the Earth, and the target is 10, which is the sun. So we get a vector from the Earth to the sun at a certain time, namely the ephemeris time for each appearance, and then in reference system in J2000. Again, also here, if you are not familiar with the coordinate systems, go back to my older videos, or at some point I will do a short refresher course. The apex direction is the flight direction of the Earth, so the direction where we are heading. And for this we are using the sun as the observer and the Earth as a target, and we use another function called spkgeo. And spkgeo is like spkgps, but it adds 3 more components into our vector, namely the velocity components in XYZ direction, so we get the velocity vector of our Earth. And computing the anti-Helian direction and anti-apex direction is, let's say, quite trivial, because you simply need to invert the vector to the sun, and you need to invert the apex vector, and that's basically it. And the next step, we can compute the different angles to see, okay, do we really get 180 degrees and 90 degrees differences? And here I did it for the Helian and anti-Helian, apex and anti-apex, and apex and Helian direction, and yeah, we get the right results, but we need the sky maps to really be sure what's going on, and also to get it in a relation with the meteors. So let's go and convert our vectors, and this is what we do here in this very complicated script. I'm yeah, I'm pretty sure you can squeeze it into a function and don't call it 4 times. It's pretty much spaghetti code, copy paste, but that's a good task for you to squeeze things a little bit because, well, you can give the 4 names anti-Helion, Apex, anti-Apex, and Helion. You could put it into a list and then iterate through the list and put it into for loop to make it a little bit more cleaner. That's maybe something for you. And to convert a vector into a coordinate system, we need the SPICE function called regret. So this is a function here. And regret gives you 3 different outputs. It gives you the distance to an object, it gives you the right ascension and the declination. And this is what we basically need. So we extract the information here by calling the list elements from the output, which is then the right ascension and the declination. And then, as you may recall from the very first script, we need to convert it into a format that is readable for matplotlib. Now, if we do all these things and we plot now our directions for a specific date, let's say, let's take only one date, you can create the animation for yourself. We have this script here where we add the anti-Helion and apex direction and so on, and then we get the following plot. We have here our radians. It is for a date at mid of June, I guess. And we see here the sun as a yellow star. We have the anti-Helion direction, which is this orange star. We have the apex direction, which is this teal triangle, and the red triangle indicates the anti-apex direction. You see around the sun we don't have any radians. Well, it's kind of difficult to observe meteors during the day. You can do it with the radio telescope, but here we have simply only visual data. But what's more important is that we have a lot of high velocity meteors. So you see them here with 60, 70 kilometers per second gathering or scattering around the apex direction. And this makes sense now because our planet is moving into the apex direction. So in addition to the velocity of the meteorites or the dust that is revolving around the sun, we have in the reference frame of the sun, the Earth's velocity is added, which means that the resulting velocity of the meteors is higher. So it appears that we are hitting the meteors with a very high speed. It's like during a snowfall where we have no wind, the sun, the snow is going down vertically. But if you drive with the car, you add a certain impact velocity into your snow. You see the gradient, of course, of the snow. We have some virtual direction where it may come from, and also the snow particles, they have a higher impact velocity. This is what you can imagine here. And the anti-apex would be, in our car analogy, the snowflakes that hit the back of our car. Now, this can only happen if we have, like, let's say, a wind from behind that is pushing our snow against the car from behind, or in our case, meteors that are catching up with the velocity of Earth and hitting us from our back. But this is quite rare, so we don't see a lot of radiance here. And additionally, we have also the anti-Helion direction, so the direction that is coming from the other side. So there is no velocity add up, yeah, there's no velocity component from the Earth or what have you. It's simply the velocity of the meteor. And now this is the distribution, and this distribution in our animation, you can create a second animation now with the script you have here, see how it distributes over the year. But this is not very satisfying, I would say, because we need to compute this distribution for every date. And the question is there a reference system where we simply can show all the data points into this apex direction or anti-apex direction independent from the time? And yes, there is a certain way to do it, and we will do this next time. We'll use SPICE for this. And if you try to search for a reference system, good luck with that, because it is not, let's say, an official reference system. But you can maybe think about it, how you could create such a reference system. And a small hint, it has to be a reference system that rotates with the Earth. Well, I hoped you learned something today in this short video, and happy coding, and see you next time.